Hi all! This episode of Physical Attraction is brought to you by the American National Standards Institute. Standards make the world go round, and they also dictate what is round. Without standardised measurements and definitions, physicists would be speaking to each other in different languages and would struggle to understand the universe even more than we already do. You can learn about standards in America at the ANSI blog at blog.ansi.org/pod to learn about how standards apply to you. Now on with the show.
Into his eyes. They're the eyes of a man.
Hello and welcome to Physical Attraction, the show that explains physics one chat-up line at a time. This episode we're still talking about Isaac Newton. It's episode 3, The Cosmic Dance. If you're from North America, you might have been lucky enough to see the recent solar eclipse. I've never been lucky enough to see totality myself, that shimmering, shining moment before everything goes dark. But I imagine there's a sense of wonder when you realise that all of the anticipation of the event has passed, and you're finally about to witness what you've been waiting for. And then, when the darkness sweeps over the land, I imagine there's another realisation. Deeper, more profound. Maybe with a little twist of primal fear from the unnatural sensation of the lights going out. That moment when you realise, for all our pretensions, for all the grandeur and guilt of the world we've built, all the solidity of the stories we tell each other, the stories called society, the stories of employment, the stories of money, the stories of safety and security. All of this could be snuffed out in an instant. The moment you realise there are things in the universe beyond our control. Things that look immutable, but aren't. That the Earth is not an isolated, eternal, perpetual place, but a miraculous spaceship hurtling through the cosmos. And you realise more than anything else, as the shadow falls over the land and the sun disappears, you realise that everything, this delicate scaffolding that we call civilization, rests on our own nuclear fusion generator, whirling through space with us, 150 million kilometres away. We're locked in a dance with the sun, and we still will be, dancing through the cosmos together, long after we're all dead. But if for some unknown reason we were plunged into darkness, and we no longer had this nourishing light, the thin veneer of that civilization would fall away. Our food would no longer be reliably delivered to the supermarket shelves. Cue mass panic, collapse, and a dark age, in more ways than one. Even knowing that eclipses are temporary, caused by a chance alignment of the sun, earth and moon, even knowing this, they still have the power to shock, amaze and even terrify. So it's no wonder that they were considered such a terrible omen. And also the occasional presence of this terrifying apparition on the skies motivated us to study the heavens in a way we might not have done otherwise. The ancient Mesopotamians had it kind of figured out just by analysing the data. They had worked out the cycle of times when the sun, earth and moon were aligned. But as you probably know, eclipses don't obviously happen everywhere on Earth at once, and as the Mesopotamians hadn't figured out the geometry of it to that extent, they didn't know the mechanics of what was going on. They just had observations, and they'd noticed the pattern. So they could tell you that there might be an eclipse on such and such a date, but they couldn't tell you where or for how long it would last. And so quite often, the dates that they predicted turned out to be wrong. There wasn't an eclipse, it was just somewhere else. In 1715, more than 300 years ago now, things got aligned in more ways than one. Edmund Halley, the astronomer, had used the new theories of Newton to create an eclipse map, one of the first of its kind. When the eclipse was about to hit Britain, he sold a map that showed its projected position across London. This wasn't just a quick way of making a buck out of his astronomy career. Halley hoped that his prediction would help people appreciate the advances made by science. Yes, get ready for some terribly formal Old English. He said, quote, "The like eclipse having not for many ages been seen in the southern parts of Great Britain, I thought it not improper to give the public an account thereof, that the sudden darkness, wherein the stars will be visible about the sun, may give no surprise to the people, who would, if unadvertised, be apt to look upon it as ominous, and to interpret it as portending evil to our sovereign Lord King George and his government, which God preserve. Hereby they will see that it is nothing more than natural, and no more than the necessary result of the motions of the sun and moon, and how well understood those are will appear by this eclipse." And on the whole, the eclipse of 1715 was a triumph. Halley was a few minutes out, but he'd applied Newton's laws to successfully predict the broad sweep of the eclipse. Newton's laws, the laws of motion and the law of universal gravitation, were good enough to put men on the moon hundreds of years later. And that program, putting people on the moon, that was what inspired Elton John to write the song Rocket Man, which led inevitably to William Shatner's cover of the song, which is arguably the greatest moment in all of human history. But seriously, Newton's laws, they are a triumph for physics that essentially enabled an entire field, mechanics, to be understood. They have given us extraordinary power because they allow us to reliably predict things mathematically. Almost all of engineering is based on Newton's laws. Humans get by in the world through a sort of direct association between cause and effect. When you're learning to play football or cricket or to walk, it's really a process of trial and error. You get more data, you get more information from your observations of the world, and you understand that if you move your legs like so, or twist the bat like this, you can achieve the desired result. What we're doing in our own strange, approximate, experience-driven way is gradually approximating, gradually getting closer to the laws of nature. So, for example, if you're trying to kick a football, you don't calculate its trajectory in your head. You don't work out how much force to apply to the football to kick it to get it to go into the goal. What you do instead is consult that vast database of previous kicks and figure out which one is the one that achieves the desired result for the situation. But at no point have you actually understood what's going on. At no point could you reliably predict or map out the trajectory of the ball. You might be able to do it roughly, but only because you're using your legs. It's not standardized. You don't know what force you're applying. You don't know what velocity it's going at. You don't know what forces act on it in the air. You just have a sort of vague sense of how nature works in reality. But you don't understand the laws behind it at all. What Newton did was understand those laws and write them down using mathematics. This means that we can make predictions about things we've never seen or touched ourselves, that we can understand the dynamics of stars and planets on the other side of the universe, as well as in our own solar system, and that we can understand how objects will behave before we invent them. And the laws of motion are valid for a huge swath of physics. They can describe all kinds of systems. They are deceptively simple. There are whole branches of physics that are almost just applying these laws to different systems. Like, for example, the whole field of fluid mechanics, a lot of it is based on applying Newton's laws to parcels of fluid. So without further ado, Newton's laws of motion, first as he wrote them in the Principia, and then in a translated form. So now for the formal Old English translation. Law 1. Every body persists in its state of being at rest or of moving uniformly straight forward, except in so far as it is compelled to change its state by force impressed. Law 2. The alteration of motion is ever proportional to the motive force impressed, and is made in the direction of the right line in which that force is impressed. And Law 3. To every action there is always opposed an equal reaction, or the mutual actions of two bodies upon each other are always equal, or directed to contrary parts. Or in modern terms we have Newton's first law: objects stay still or moving in a straight line at a constant speed unless a force acts on them. Newton's second law: when a force is applied to an object, it accelerates in the direction of that force, at a rate proportional to the force. And Newton's third law: action is equal and opposite to reaction. So what these laws actually do is they give us a framework for understanding how things move. They pretty much define a force. It's something that can cause a body to accelerate. Newton was thinking of pushes and pulls, the physical forces that we understand that you can exert on objects. He was probably also thinking about gravity at this stage too. But we now know about electromagnetic forces and nuclear forces too. Newton's first law tells us that, basically, only forces can change the velocity, that's the speed and direction of movement, for an object. Without forces acting, things will carry on going in the same direction forever. Aristotle, whose word had been law before the 17th century, he insisted that if nothing continued to propel an object, it would eventually stop moving. So, effectively, to keep objects moving, you need to carry on pushing them. Of course, this makes intuitive sense in our world, which is full of friction and air resistance and things that like to stop moving. But it's not true. Things stop because unbalanced forces act on them. Newton gave credit to Galileo for this one because, as we discussed in the first episode, He'd really come up with this idea first. But again, it's non-intuitive, and it goes to show you how clever these people were when they figured out what they figured out. Then there's the second law. The first thing I remember being told when I came into undergrad physics is that Newton's second law is really a differential equation. And this is the power of Newton's second law, really. We talked about how differential equations deal with how things change, and solving them allows you to make predictions. In the same way, Newton's second law tells you that if you know the force acting on an object, and you can express it mathematically, then it's just a matter of mathematics to work out its acceleration. You just divide by the mass, it's that simple. So obviously you have a consequence like this, that the heavier something is, the bigger a push you need to give it to make it accelerate by the same amount. That's fairly intuitive. But the fact that you can actually calculate the acceleration from the force is really important. Because as we said, once you have acceleration, you can integrate to get speed. And once you have speed, you can integrate to get position. So you can calculate where the object has been and where it's going to go, anything you might want to know about its motion, providing you know the forces that act on it. So this is incredibly powerful because it allows us to predict the future. And something complicated, like a fluid dynamics equation like the Navier-Stokes equation. The Navier-Stokes equation is mathematically impossible to solve without using a computer. You can simplify it into certain regimes where you can solve it, but in actual fact, it's got incredibly complex dynamics, it can behave in bizarre and turbulent ways, and you need quite complex computers to get numerical solutions to it. But it's really just Newton's second law applied to a moving parcel of fluid. Anyway, more on that for another episode. So Newton's second law often gets expressed as F equals ma. Here we use the algebra convention that two letters next to each other is multiplication. So this is force is mass times acceleration, which instantly defines this strange thing called mass, which is not quite the same as weight. Mass is basically a measurement of how much you resist accelerating when someone applies a force. It's how difficult it is to push a particular object. These ideas will be familiar to anyone who's ever kicked the ground instead of a football. Just me? Maybe it's a physics thing, I don't know. The third law says that action is equal and opposite to reaction. Now this is really easy to misunderstand. But essentially what it's saying is that when you push on a wall, for example, the wall pushes you back with the same force. People sometimes get confused about the third law, action is equal and opposite to reaction. They'll say, I'm standing on the ground. Earth is pulling me down. It pulls on my mass, and I call that force weight. The weight pushes into the floor, and the floor pushes back on me. So the opposite reaction to my gravity is the reaction from the floor. Action is equal and opposite to reaction. That's not quite true. Actually, the reaction to the Earth's gravity pulling on you is your gravity pulling on the Earth. The reaction to you pushing into the floor is the floor pushing back on you. So there's more forces to consider here than you might have initially thought. By the way, it's always been a fascinating question for me that turned out to be really hard to get a straight answer to. Why don't we fall through the floor? Seriously, we know that the atom is just 99.9999% empty space. We covered that in our episodes on atomic physics. So why don't we just fall through objects when there's such a low chance of the nuclei of our atoms aligning and colliding? And also, we're all familiar with the fact that you can push on objects and exert forces of your own. But you also probably know that there are 4 fundamental forces: electromagnetism, gravity, and the strong and weak nuclear forces. So what's the force that stops you from falling through your seat, the reaction force? It seems weird that the forces we're most familiar with, the pushes and pulls, aren't one of the 4 fundamental forces. What kind of a force is that? You can see people give 2 different answers. One of them is basically correct and the other one is basically wrong, but they're fairly similar to each other in some ways. So the 2 answers that people give is that it's either electrons, the electrons in the atoms of your body, say, and the atoms of the seat, pushing against each other by electromagnetic repulsion. Or they say it's Pauli exclusion, a quantum mechanical effect, which means that you can't force electrons too close together. We talked about this way back in the early episodes on stellar formation, hot and heavy, right at the start. Do you remember that after a star dies in a supernova, it collapses in on itself? But in some cases the collapse is halted by, in the case of a white dwarf or a neutron star, And it's because of these Pauli exclusion. It's because these stars can't collapse any further, because their particles don't like being squished together. So in the case of a neutron star, you'll remember the episodes we did about the Nobel Prize that was won for colliding neutron stars, where I talked about what neutron stars are. And they're being held apart by this Pauli exclusion principle, which means that their neutrons don't like being forced together, and that pushes to counterbalance the gravity. So it turns out that this electron degeneracy pressure, electrons not liking being forced together, is actually a big part of these day-to-day forces. You can find people who will tell you both the electromagnetic and the Pauli explanation, but it seems like electron degeneracy is more important. Although it took until the 1960s, when Freeman Dyson calculated it, to really understand the solution to this problem. So it's incredible to think that until the 1960s, physicists couldn't tell you why we don't just fall through all the empty space in atoms towards the centre of the Earth. And that you actually need quantum mechanics to explain that. You need quantum mechanics to explain what causes the pushing force when you push on the seat, and what causes you to stop falling through the floor. I think that's incredible. Anyway, back to Newton's laws. We have the three laws. Later, these laws would be re-expressed in terms of momentum. It turns out that momentum, the mass multiplied by the velocity of the object, is a very important quantity. It's conserved in any interaction. And Newton's laws, in many ways, are all laws about momentum. The first law says that if no force acts, momentum is conserved for a single object. That is to say, the single object will carry on going in the same direction, at the same speed. The second law says that the force is the rate of change of momentum. How quickly your momentum is changing depends on the forces that act on you. Newton didn't appreciate when he wrote it that momentum can change for two reasons. You can speed up or your mass can change. And the third law, the one that says that action is equal and opposite to reaction, is also just the conservation of momentum overall. Since momentum can't change overall, forces have to be equal and opposite. Imagine two objects pushing on each other, so for example, a collision. If they don't push in opposite directions with equal force, then you're getting some momentum for free. Instead, the forces are equal and opposite. If one object gains momentum, the other has to lose it. If we had two balls colliding with each other of roughly the same speed and weight and mass and so on, then we'd expect them to stop. We wouldn't expect one of them to suddenly fly off in one random direction. That's because momentum is conserved. And so any momentum gained by one object must be lost by the other object. So in effect, when they both come to a stop, it's because they've exchanged momentum totally, and now neither of them have any net momentum in any net direction. So momentum is conserved, and that's the third law. There we go, Newton's laws. On the surface, fairly simple, but a whole world of consequences. And now we have to talk about his most famous discovery of all. So it kind of annoys me when people say that Newton discovered gravity. I know they mean it as shorthand, but it kind of implies that for thousands of years before Newton, people hadn't noticed that stuff falls to the ground when you drop it. This is obviously not true. The Greeks knew this, for example, along with everyone else, and they called it gravitas, which now means something slightly different. Nowadays it means something that politicians don't have. What Newton did was understand how gravity worked, at least mathematically. So this is from the Royal Society, written by a friend of Newton. Quote, "After dinner, the weather being warm, we went into the garden and drank tea under the shade of some apple trees. He told me he was just in the same situation as when formerly the notion of gravitation came into his mind. It was occasioned by the fall of an apple as he sat in contemplative mood. Why should that apple always descend perpendicularly to the ground, he thought to himself. So no, the apple didn't hit him on the head. But yes, there was an apple, or at least Newton said there was one. I think this is just a poetic way of putting it, to be honest. Newton's theory of gravity probably didn't come to him in a flash of inspiration like this. But that kind of divine intervention would have appealed to his sense of drama, and maybe his ego too. But chances are it was a longer process of thinking about gravity and trying to come up with a consistent theory to explain it. And, we know that Newton was constantly thinking about how the world worked, constantly trying to explain the things that he saw in the world. So the idea that the first time he thought about gravity was when the apple fell is a little bit strange, I think. And saying that Newton discovered gravity really irritates me. Of course he didn't. People knew that things fell down. And further, they knew that objects in the heavens were moving. After Copernicus, they even knew that the Earth was orbiting the Sun. What they didn't have was a consistent theory that explained why. But it was the motion of the planets, more than the motion of any apples, that confirmed Newton was right. So Newton's law of gravitation, which was published in the Principia, says that every object with mass attracts every other object with mass. It pulls on them with a force, and that force depends on the masses of the two objects multiplied together, divided by the distance between the objects squared. So that's the masses of the objects multiplied together, divided by the distance between them squared. So clearly the square numbers get big quite quickly. You start with 1, 4, 9, 16, 25, 36, and it goes on. So if the objects are twice as far apart, the force of gravity is 4 times weaker. For this reason, the dominant force of gravity for you is the Earth pulling down on you. That's your weight. The Earth is a sphere, and Newton worked out that mathematically his law meant that spheres act like all of their mass is concentrated at the centre. From the outside, it's kind of the same as if all the matter was a blob in the middle. So you're actually being pulled towards the centre of the Earth, which is about 6,400 kilometres away from you. I know that because that's the rough radius of the Earth. And because action is equal and opposite to reaction, and gravity conserves momentum too, you're also pulling the centre of the Earth towards you. But the Earth doesn't really notice while you're stuck on the ground. So we require airplanes, spaceships and trampolines to temporarily free ourselves from the gravitational pull. Suddenly, with the law of universal gravitation, everything made sense. Remember Kepler's laws? The laws that told us that the planets moved elliptically and so on? Newton could rederive them all now. The inverse square law gave you elliptical orbits for the planets and explained their motions in the heavens almost perfectly. The sun pulls inwards on the planets, which pull outwards. Like if you're whirling a lasso around, you pull inwards towards the centre to drag it in a circle or an ellipse. The mathematics of the orbits meant that equal areas were swept out in equal times. This is because angular momentum is conserved in the orbits. Turns out to be a direct consequence of that. And the time period of the orbit related to the distances in just the right way under Newton's laws. You can do some fairly simple calculations if you assume the orbit is circular and you assume the formulas for centripetal force and so on, and you can find out that these orbits obey Kepler's laws too. In fact, Newton's law of gravitation meant that by measuring the time period of the orbits in the planets around the Sun, they could map out the distances in the solar system. The law of gravitation was an incredible triumph. F equals gmm over r squared. Get it tattooed on your chest. And while Newton was feuding with Hooke over who came up with the inverse square law first, I'm not going to get into that little debate either. Hooke was working on gravity and celestial mechanics as well, but I don't know that he got quite as far as Newton did. Physics was faced with a problem. Because Newton's gravitational law worked incredibly well. It predicted the way the world behaved to within tiny margins of error. It explained people's weights, it explained the force that they pushed down on the Earth with. It explained how the stars and planets moved. It could explain all kinds of things about comets as well. It opened up a whole new field of study and understanding. And for most interactions, this law is all you need to understand gravity. We still use the same law for rough calculations of stellar orbits and so on today. With Newton's laws, you can get men to the moon. That is true. They did not need anything other than that. So it was clearly good physics, it was just so correct, and it explained nearly every observation they could make, and it stood up to all the tests of logic and experiment. There was no way of disproving Newton's laws that early on. People couldn't quite figure out how they could possibly be wrong. It was one of the most experimentally observed and confirmed theories of all time, used to build foundations for so much of future human civilization, but philosophically it left something to be desired. This reminds me a lot of when quantum mechanics was discovered, which we'll cover soon. Essentially, it's the same problem. They find this theory mathematically that explains everything wonderfully and makes amazing predictions. But no one understands why it works. In fact, there's something very strange about it. It seems quite illogical. The mathematics of it is beautiful and wonderful and seems to describe nature very well. But they can't see why it makes sense. And it was maybe only the fact that Newton believed in the occult and weirdness and strange things beyond our understanding that allowed him to come up with a theory of gravity and be happy with it. To understand why it was so distressing, think about just how weird gravity is. I am attracting you with a gravitational force right now, whoever you are, wherever you are. If I know how far apart we are and how much you weigh, I can calculate that force. It will be tiny, obviously, but it does exist. There is an influence between you and me and every object that you're looking at now, and you and every object that you're looking at now. Everything. You're pulling on the sun and Mars and the volcano Krakatoa and the Empire State Building and your favourite celebrity and stars and planets in the far-off distant universe that you've never even seen. Never ever allow yourself to forget just how weird and amazing this is. It is a way that you're, in a sense, at one with the universe, with people you've never met, places you've never seen, with neutron stars and strange suns far away, all feeling your force and sending theirs back to you. How can it be possible that every object with mass in the universe knows about every other object with mass? At the time, they didn't know, as we know now, that gravity travels at a finite speed, the speed of light. And so people were trying to measure the speed of gravity, and they couldn't measure it. It was far too fast. So communication of the motion of objects is not actually instantaneous. On the scales of our solar system even, it doesn't matter all that much. On the scales of our planet, it doesn't really matter at all. The travel time for gravity is not that important. But gravity was still incredibly strange. It didn't behave like the other forces. There was no obvious reason why there was action at a distance. All the forces that they were used to at that time seemed to be more obvious. Things pushed and pulled on each other because they were touching or colliding, or maybe because little particles streamed out and bashed into things physically. But what was gravity? That wasn't anything like this. Was it little grappling hooks that spread between every pair of objects in the universe, pulling on both of them at the same time? Tiny strings connecting you and the everything? Newton didn't know, and it worried him. Newton said, quote, "That one body may act upon another at a distance, through a vacuum, without the mediation of anything else, by and through which their action and force may be conveyed from one another, is to me so great an absurdity that, I believe no man who has in philosophic matters a competent faculty of thinking could ever fall into it." But he never was quite able to work out what it was that was communicating gravity, why it was that gravity behaved in the way that it did. Instead, he did what the early scientists of quantum mechanics did with the aspects of their theory that they didn't like so much. He eventually gave in and said, "All that matters is that it works, so it must be true. Why can come later, or maybe not at all." He said, quote, "I have not yet been able to discover the cause of these properties of gravity from phenomena, and I feign no hypotheses. It is enough that gravity does really exist and act according to the laws I have explained, and that it abundantly serves to account for all the motions of celestial bodies." In Newton's defence, as we've mentioned, gravity is still a problem. We still don't really know if it's communicated via particles or not. There are still huge mysteries surrounding gravity, so perhaps it's not too much of a failure on his part not to understand it in the 17th century. He knew that it worked, and that was enough to ensure his place in scientific history. He knew how it worked, and that was enough to send rocket men to the moon. Why it worked, and by what mechanism? In some ways, it's still an open question. Thanks for listening to this episode of Physical Attraction. Next episode, in our final show on Newton, we'll be dealing with his other discoveries and writings, his dives into alchemy and the occult, his personal life, such as there was one, and that one time he was put in charge of printing all the money in Britain. Until then, you can follow us on Twitter @PhysicsPod. Visit the website www.physicspodcast.com. I highly recommend you do these things and ask us all the questions that you like. Also on Twitter you'll find the link to the PayPal, which is www.paypal.me/physicspod, where you can donate to the show if you've been enjoying what we're doing so far. I do all of this for free, I pay my own hosting costs, that kind of thing. So it would be really kind of you if you've enjoyed what we do to support us a little bit that way. And if you can't support us like that, that's fine. But what I would ask you to do is just tell one other person about the show. Because as I say every time, if everyone tells one person about the show, it won't take long before we've got trillions upon trillions of listeners. And when we have trillions of listeners, our exponential growth will stun the world. Believe me, it's going to happen. Until next time, stay safe.
Pornographic tastes. A Marquis de Sade would have regarded as a peer.
She packed my bags. Last night, pre-flight. 0 hour. 9 a.m. And I'm gonna be high as a kite by then. I miss the earth so much. And I miss my wife. It's lonely out there in space. On such a timeless flight. And I think it's gonna be a long, long time till touchdown brings me round again to find I'm not the man they think I am at home. Oh no, no, no. I'm a rocket man. Rocket man. Burning out his fuse out here, alone. And I think it's gonna be a long, long time till touchdown brings me round again to find I'm not the man they think I am at home. Oh no, 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 no. I'm a rocket man. Rocket man. Burning out his fuse out here alone. Mars ain't the kind of place to raise your kids. In fact, it's cold as hell. And there's no one there to raise them, if you did. And all this science, I don't understand. It's just my job. 5 days a week. A rocket man. A rocket man. And I think it's gonna be a long, long time till touchdown brings me round again to find I'm not the man they think I am at home. Oh no, 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 no. I'm a rocket man. Rocket man. Burning up his fuse out here alone. And I think it's gonna be a long, long time till touchdown brings me round again to find I'm not the man they think I am at home. Oh no, no, no. I'm a rocket man. Rocket man. Burning up his fuse out here alone. And I think it's gonna be a long, long time. And I think it's gonna be a long, long time. And I think it's gonna be a long, long time. And I think it's gonna be a long, long time. And I think it's gonna be a long, long time. And I think it's gonna be a long, long time. And I think it's gonna be a long, long time.